two matrices A and B are orthogonally similar if there's an orthogonal matrix P such that the transpose of P multiplied by A multiplied by P is equal to B. So recall when we defined two similar matrices, we had a matrix P that was not necessarily orthogonal. So we had P inverse by A by P is equal to B. And furthermore, the matrix A is orthogonally diagonalizable if the transpose of P multiplied by A multiplied by P gives a diagonal matrix. So in other words, we say P orthogonally diagonalizes A. So note that the only matrices that can be orthogonally diagonalized are symmetric matrices. So in other words, A is equal to its transpose. So this can be shown if we rewrite this equation by pre-multiplying both sides by P and post-multiplying both sides by P transpose. So that gives A is equal to P by the diagonal matrix by P transpose. And if we take the transpose of both sides, we have the transpose of PD P transpose. So we can first transpose this part and multiply by the transpose of P. So we have dP transpose transposed by P transpose, and therefore the left hand term is the transpose of P transpose multiplied by D transpose, which is equal to D because D is a diagonal matrix, and multiplied by P transpose, which gives P multiplied by D by P transpose. So that means that A transpose is equal to A. And the only way that's possible is if A is symmetric. So a square matrix A having the same number of rows as columns is orthogonally diagonalizable if it has an orthogonal set of eigenvectors and if it's symmetric. For a symmetric matrix A, so basically A is equal to its transpose, the eigenvalues are all real numbers and the eigenvectors from different eigenspaces are orthogonal. So if you consider this symmetric matrix, we can solve the characteristic equation to get the eigenvalues. So we have the determinant of 2 minus lambda on a diagonal, and the off-diagonal entries remain the same, and that's equal to 0. So therefore, we have 2 minus lambda squared, minus 1 is 0. So that gives lambda squared minus 4 lambda plus 4 minus 1, which is plus 3. And that's equal to 0. And then if we factor the left polynomial, we have lambda minus 3 by lambda minus 1 is 0. So our eigenvalues are lambda 1 is 3 and lambda 2 is 1. And therefore for our left eigenvalue, we have our matrix A minus lambda I, as we've seen previously, has entries of 2 minus lambda on the diagonal, and 1's off the diagonal, and that's multiplied by the vector with entries v1 and v2 is equal to 0. So therefore we can solve this equation by adding row 1 to row 2. So you'd get zeros in the bottom row, and therefore we have minus v1 plus v2 is equal to 0 from the first equation. And therefore we can set v2 as a parameter t, and therefore v1 is also equal to t. So therefore all eigenvectors in the eigenspace corresponding to this eigenvalue can be represented as follows. So we have v1, v2 is equal to the parameter t by the basis vector. And for our second eigenvalue, we have 2 minus lambda and 2 minus lambda, giving 1's on a diagonal. So again, subtracting row 1 from row 2, we'll get zeros in row 2. So we're left with v1 plus v2 is equal to 0. And if we set v2 as a parameter t, then we get v1 is minus t. So therefore each eigenvector in the eigenspace corresponding to lambda 2 can be written as t multiplied by the basis vector with components minus 1 and 1. So as we saw, the eigenvalues are all real for a symmetric matrix, and all the eigenvectors from the different eigenspaces are orthogonal to each other, as we can see. Let's look at a process for orthogonally diagonalizing a symmetric matrix. So step 1 is to find a basis for each eigenspace. So as we've done previously, we first find the eigenvalues. So here we have 2 repeated eigenvalues. So we only need to find the eigenvectors corresponding to one of those eigenvalues. And from that, we find the following 2 basis vectors for the eigenspace corresponding to lambda equals 1. And similarly for the other eigenvalue, we find a basis vector for the eigenspace corresponding to it. So I'll leave this part for you as an exercise. So as we can see, for a symmetric matrix, all the eigenvalues are real, and the eigenvectors between the 2 eigenspaces are orthogonal. And this can be verified by taking the inner product of this basis vector with the other 2 basis vectors, which you'll see evaluates to 0. But as we can see, the basis vectors in one of the eigenspaces are not necessarily orthogonal. So the next step is to apply the Gram-Schmidt process to each of these different bases to obtain an orthonormal basis for each separate eigenspace. So starting with this eigenspace, we set the first orthogonal vector to be equal to the first basis vector, and then the next step of the Gram-Schmidt process involves taking the second basis vector and projecting the second basis vector onto the first orthogonal basis vector. So using the inner product, we obtain -1, 0, 1. And we take the inner product of this with O1. And this is divided by the squared norm of O1 and in the direction of O1. And therefore, to obtain a perpendicular vector to O1, we subtract the projected component of this basis vector onto O1 from this basis vector. So this gives the orthogonal component to O1. And if you do the algebra, the inner product evaluates to 1. And the square norm of this basis vector is √2 squared, which is 2. And therefore 1/2 multiplied by this vector gives -1/2, 1/2, and 0. So finally we have -1 plus 1/2 is -1/2, 0 minus 1/2 is -1/2, and 1 minus 0 is 1. And now we can normalize these two basis vectors to obtain an orthonormal basis for this first eigenspace. So the norm of this vector is √2. So normalizing this basis vector, we get -1 on √2, 1 on √2, and 0. And the norm of this vector gives the square root of 1/2 squared plus 1/2 squared plus 1 squared, which is √6 on 4, or the square root of 6 on 2. And then dividing each component by this value, we get -1 on √6, -1 on √6, and 2 on √6. So you can verify that these two vectors are orthogonal by evaluating the inner product. And recall that step 2, we wanted an orthonormal basis for each eigenspace. So for this basis vector, for the eigenspace corresponding to this eigenvalue, the norm of this vector is √3. So we just divide each component by √3. So we get 1 on √3 for each component. And then in the third step, we form the matrix P by putting the orthonormal eigenvectors from step 2 in each column. And let me copy this matrix across because we'll need it later. So we had our first basis vector from the first eigenspace in column 1, and the second basis vector from the first eigenspace in column 2, and the third basis vector comes from the second eigenspace. So all these three vectors are orthonormal. which is our matrix P. So given our matrix A, if you transpose P and multiply it by A and then by P, you'll get a diagonal matrix, and each entry on a diagonal of this matrix gives the eigenvalue corresponding to each of these eigenvectors. So the first two orthonormal eigenvectors correspond to the eigenvalue of 1, and in the final column, this eigenvector corresponds to the eigenvalue of 4. So this is the diagonal matrix that you'll get. And I'll leave it for you to verify this as an exercise. Recall that we found a symmetric matrix that was orthogonally diagonalized by a matrix P, where P had the unit eigenvectors in each column. So we had V1, V2 up to Vr, where R is the number of rows of the symmetric matrix, and we had the eigenvalues lambda 1 to lambda r correspond to each of those eigenvectors. So in this case, we know the diagonal matrix D, which was equal to P transpose by A by P, is the matrix with those eigenvalues in the diagonal positions. And therefore, if we turn this around for the matrix A, which was equal to P by D by P transpose, so effectively what you do is transpose P and multiply it by D, being this matrix of eigenvalues on a diagonal, and multiply by P transpose, and you obtain the following result, being the first eigenvalue by the unit eigenvector by its transpose, plus a second eigenvalue by V2 hat by the transpose of V2 hat, and so on up to lambda r by V hat r by its transpose. So this here is the spectral decomposition of the matrix A, and noting the product of the vector with its transpose will give a square matrix. Then this matrix is the standard matrix for the orthogonal projection of the vector space of R tuples on the subspace spanned by the vector V1 hat. And this will be the standard matrix for the orthogonal projection on the subspace spanned by V2 hat, and so on. And let's visualize this geometrically. So first you find the eigenvalues, and then the basis vectors for the eigenspace corresponding to each eigenvalue. And these vectors will be orthogonal. And then we normalize these vectors, so we get V1 hat is 1 over the square root of 1 squared plus 1 squared. So that'll be 1 on root 2 and 1 on root 2. And then normalizing the other eigenvector, we get a unit vector with components of 1 on root 2 and minus 1 on root 2. And then to obtain a spectral decomposition of A, we multiply the eigenvalue, lambda 1 equals 3, by V1 by its transpose. And then if you evaluate this product, you'll get 1 half, 1 half, 1 half, and 1 half. And then the next eigenvalue is 1. And this time we multiply vector v2 hat by its transpose. So we'd get 1 half, minus a half, minus a half, and 1 half. So this here is a spectral decomposition of A. Now suppose we have some vector with components 1, 1. So essentially multiplying this vector by the matrix A will give 3, 3. So the vector would look something like this. Now the eigenspace spanned by vector v1 hat is the straight line through the origin along the direction of that vector. So this unit vector looks something like this and has components 1 on root 2, 1 on root 2. And then the other eigenspace spanned by this basis eigenvector looks something like this. So both eigenspaces are orthogonal. So the basis vector for this case has components 1 on root 2 and minus 1 on root 2. So as we can see, if we multiply this first matrix by our vector 1, 1, then it projects its vector onto the red eigenspace spanned by this eigenvector. So here, our vector 1, 1 is already in the first eigenspace. So the projection matrix effectively does nothing. So we get 1 half plus a half is 1, and 1 half plus a half is 1. So we get the same vector back. And then if we multiply it by the eigenvalue, that gives our vector 3, 3. And then for this second product, in the spectral decomposition of A, if we multiply this by 1, 1, we get the 0 vector. So essentially, because our original vector 1, 1 was in the first eigenspace, and the second eigenspace is orthogonal to this eigenspace, then the projection of this vector onto the second eigenspace is going to give the 0 vector. So essentially, we have two ways of obtaining the image of our vector under multiplication by a symmetric matrix. So we can multiply it by the symmetric matrix directly, or we can project it onto each eigenspace and then stretch it and sum those transformations for each eigenspace, which we've seen geometrically.